Good afternoon to everybody who is currently in this session on avionics that you are crediting as an elective. So we are actually in the concept and introductory stages of what constitutes a typical avionics system. Okay, so how the component level progress has been across the evolutions as a decadal increment. Okay, and this particular slide actually portrays that in terms of an evolution over a 10-year time frame, over which the various technologies, right from the very basic, which is not even mentioned here in the form of tube-based devices and valves, is being replaced with the advent of transistor technology. Okay, small scale to medium and large scale, and the very large scale integration, which in effect identifies the components and interconnects in the dimensions of nanometers. Okay, and from there onwards, you have application specific ICs, which in a sense are trying to identify functionality associated with which there is an integrated circuit design. Okay, and beyond that point, you have the hybrid ICs or the multi-chip modules and circuit level integration as the most recent technology that has been realized with the scale of implementation going below 4 nanometers. Okay, so that is effectively the increased packing factor realization as a function of the time scale over which the technology has progressively been refined to the extent that now you have extreme miniaturization and the concurrent advantage in the form of the size, weight, power, and cost SWAP-C criterion, which has also tremendously advanced with the transistor technology and its evolution. All right, related to this discussion is the actual methodology when it comes to the design of avionics systems, which is primarily enabled using the concept known as packaging. Okay, so how does one functionally define the boundaries of a specific subsystem or a module that goes into a larger assembly or integration exercise when it becomes an avionics system? Okay, so what is the typical progress in technology that is identified at the level of packaging the avionics? So if you look at a typical implementation of an avionics subsystem, and there are so many of them, and we'll also be looking at a massive list of the various subsystems and avionics systems as it is. So to start with, let's effectively consider a situation where the aircraft, other than the mechanical and the aspects of structural implementation of an airplane, are going to be deconstructed, okay, or disassembled in a manner where you can literally give a exhibition of the various components. Okay, so that's exactly what is being shown here. So in a form where it is completely integrated with the airframe, what you notice is on the left-hand side, both the viewgrams that you're seeing. Okay, so the first one on the top left-hand side shows a typical avionics system that is primarily meant for navigating the airplane. Okay, and especially the one that has to do with taking the airplane through inclement weather. Okay, so as a realization of that, you have a radar system that is shown here. The front end is a typical phased array antenna, and the electronics that is used to control the steerability of the antenna beam. The mechanical aspects, if there are any, that are used to turn the antenna physically if required. And along with that, you also have the various electronic systems which are used to actually control and acquire the information that has been obtained from such an avionics system, okay, which in turn is going to handle the signals at various levels as part of the signal conditioning, modulation, encryption, and so on, signal generation and such like aspects before the actual information that is being retrieved after a suitable external parameter is being monitored on a near continuous basis. The analysis is being pursued using a dedicated scheme of computation, after which the information is projected to the person who controls the airplane. Okay, so the pilot is the one who has to make a wise decision based on the various inputs that are being received, which are primarily enabled in the form of realization of the electronic subsystems. Okay, so on the bottom left, there is an analog implementation of the type that is used to not just monitor the weather, but various other parameters of the airplane, such as its attitude parameters, the control surfaces, their deployments, the rotation of the power plant and the engine, which in turn directly translates into the suitable amount of power that can be derived for not just propelling the airplane or creating a suitable level of lift and maneuver, but to also energize the various electronics. Okay, so the onboard power is generated from the power plant that is in operation, which could be of a type that is either propeller driven or jet engine driven. Okay, both possibilities. And in more advanced aircrafts, you also have rocket powered power plant systems. Okay, all right. So that is the evident presence of the instrumentation that is used to monitor the various subsystems and their performances. And subsystems needn't always be electronic in nature. Okay, so you have the concept of the control surfaces, parameters of the external world, the attitude parameters that the aircraft needs to maintain in order to precisely navigate over a specific phase of the flight characteristics, okay, such as the taxiing, the ascent, the takeoff, the climb, the cruise phase where it is in a level flight performance attribute, then the descent and the landing, and again a taxiing phase. So these are all varying phases in the operation of the airplane. And during each of them, the various subsystems need to provide accurate information. All right, so on the right-hand side, you have the instrumentation itself, which has been disassembled or so-called deconstructed in order to reasonably make sense of what has all gone into a very tight packaging configuration, okay, in the limited space that is available. So you can find by and large significant number of these subsystems which have been integrated, which means they are connected one to the other using the less numbers of connectivity solutions, such as transmission lines and wires, which will be used to connect one to the next subsystem. Okay, so these have all been formed out in a manner where one can easily see plenty of the electronics that has been in turn accommodated within the limited space that is available within the airplane. Okay. Right. So the important standard that has to be understood in terms of packaging technologies, because there are standards which have been defined in earlier times based on the manufacturer of the airplane, and there were a few. And it has now reached a point where it is reasonably consolidated in terms of the actual company that integrates the various solutions that have been provided from the various vendors. Okay, so what typically is been identified in the form of a Boeing Aircraft Corporation, whose headquarters is in Seattle, or the Airbus industry, whose headquarters is in Europe, more so in a place called Toulouse in France. So all of these companies, what they effectively do is bring together the various engineering solutions which have been designed and manufactured by as many vendors, okay? And each of the vendors may have a competitor against whom they'll need to show a reasonable level of advantage and benefit out of incorporation of their product, okay? So that they can stand some chance against their competitor who also offers a similar product, okay? So that advantage has to be primarily demonstrated in terms of various performance metrics. One of them is the actual size, weight, power, and cost criterion, SWAPC. Okay, In addition to that, it also has to demonstrate various other metrics, and we'll be looking at that as a separate discussion phase as part of this course. Okay. In any case, so each of these vendors has some standard in terms of the packaging scheme alone, if it were to be considered a particular aspect of the design. Okay. So some of these standards are the concepts defined in terms of packaging in the form of line replaceable units, LRU. Okay. Line replaceable units are one of the standard schemes for packaging that have been identified over the course of time in avionics systems. And these were developed as a way of removing functional elements from the avionics system with a minimal disruption that it can create. Okay. In the scenario where it involves upgrading a particular subsystem or a block of the implementation, or if there is an issue with that particular implementation block, if there is a reason to extract it out in order to service it, the ease with which it can be attempted is primarily realized by having it already introduced in the overall scheme in the form of modules. Okay. So one of the standards for these modules, or the so-called packaging level implementation of the electronics, is the line replaceable unit. So the LRUs are logical and functional boundaries which are associated with the tasks that they are destined to perform within the larger avionics system and within the aircraft also. Okay. So there are two broad divisions of this concept of the line replaceable units. One of them is called as the air transport radio, ATR. So you will notice that packaging comes in various standards which are specified as either ATR with a alphanumerical representation following that. And there is yet another scheme that is implemented, which is called as the modular concept unit, MCU. So it is either as ATR or MCU that you will have the line replaceable unit configuration defined in aircraft systems. Right, so here is an example of where you will find a typical solution which is neatly packaged already in aircrafts of recent type, such as the 777 of Boeing. Okay, right. So right in the forefront, at the tip of the airplane, in the right front area, you have the flight test and system monitoring, which is used to either monitor the performance of the various aircraft's critical technologies in live terms while the aircraft is in flight. Of course, it makes use of satellite communication for that purpose, so that various vendors can, in a dedicated manner, assess the performance of their particular product in real time, okay, through satellite communication technology. So you also have, apart from that, display solutions which are there within the region occupied by the pilot. The crash data recording in the event the aircraft has met with a calamitous situation. There is a constant recording that is maintained in the form of the flight data recorder and the cockpit voice recorder. So one of which is shown here in the form of the crash recorder scheme. Okay. So you also have an implementation of a similar type that is located in a reasonably safe and secure region, which is close to the tail section of the airplane. Okay. These are formed out in a manner where they can completely record the various events, including voice recordings in the cockpit that have happened over a certain duration of time over which the aircraft had been in flight. Okay. So you also have the avionics display solutions and the video recording that takes place of regions which are in the immediate vicinity of the airplane, as well as in the cabin region of the aircraft, okay, within the available space on board the airplane. Okay, that could include regions occupied by passengers as well as by the cargo. All right, so you have the recording of the information taking place of various other critical components as well in the form of signal parameters. Okay, so you have various sensors and the processing of the information coming from the sensors, because the rates at which the information reaches the avionics bay from the various sensors is going to be different. For example, air data monitoring sensors work at higher data rates, which means per second they create a massive number of data points. Okay, while some other parameters such as the height parameters and all need not work on such a high data rate, because heights are typically calibrated in the order of few tens of meters, and anything within that range would not be adequately covered. So these kinds of variabilities of the parameters that are being monitored by the various sensors is constantly being processed, and the information is processed at a really high rate. Okay, video information and video processing parameters are critical to such tasks. So you have the dedicated processors for the information as well as for the data that is generated in various forms as time series data, as well as two-dimensional and three-dimensional information components. Okay, so the processing systems exist for that, which are very dedicated to the task of the nature of the sensors that are integrated to such processors. So radar processing for the purpose of identifying potential issues with cloud formation and weather patterns, which will need to be carefully navigated, weather radar systems, as well as objects which may likely impact the aircraft. So abilities to monitor various other targets in the immediate and reasonable vicinity regions of the airplane. Situational awareness is the term that is used here. So radar processing makes use of specific parameters such as Doppler shift and potential target designation requirements, classification of targets. Each of this is a dedicated activity. And for this, you have exclusive computational processors that work as the radar processing schemes. So abilities to offer interconnects and mediation for signal travel from the various sensors to the processors is enabled using networks and dedicated controls for such information flow pathways, or the so-called networks, and the connectivity solutions that exist, which are mostly redundant, in a manner where if one pathway fails, there is still the possibility to get ahead with the actual data available from the various sensors. So that kind of a redundant pathway for interconnectivity that exists between the various sensors and the processors and the avionics display solutions is again one more aspect that is governed by a network link scheme that is implemented on board. Okay, so various parameters of carefully monitoring the flight characteristics, such as the attitude parameters, pitch, yaw, and roll aspects, the typical distance that the aircraft maintains with reference to the terrain. Okay, in turn, how are these used to enable the various control surfaces depending on turbulence factors which may exist while the aircraft is flying, and so on. So these are all monitored and controlled by another computing environment, which is called as the flight control system, FCS. Okay, as you can notice, there is a specific form factor and a packaging scheme that is identified for them. Okay, we are going to look at some of the details in terms of the implementation of the packaging schemes for each of this. Beyond this point, we will look at the standards that are adapted as part of the design phase of the subsystems. Then we will go into the integration. And as a final discussion for this course, we will be looking at the sensors as well. Okay, so that's the systematic buildup that we will be having for approach to how this course handles the various avionics systems, starting with the concept of packaging. All right, so I mentioned about the concept of the line replaceable units. These come in two forms. They are either implemented as the air transport radio or the modular concept unit. So we'll be looking at the concept of the ATR, okay, before we come to the MCU scheme. So what is the air transport radio? Okay, so ATR is a standardized scheme for racking or placing the various packages or neatly configured box configurations into a standard rack, okay, which carries several such boxes, which can be easily connected, and they occupy a very systematic configuration or arrangement or presentation in the region of the aircraft called the avionics bay. Okay, so the ATR is a standardized racking system, and it follows what is called as the Aeronautical Radio Incorporated (ARINC) standard that is identified in the form of 3 module dimensions, okay, or sizes, which may be either half ATR, 1 ATR, or 1/2 more than the standard ATR configuration, okay. So in all of these specifications of height and length, you have the standard packaging configurations which are identifiable. So there are standards which are enforced in the aspects such as connectors and pin sizes, and these are specified along with the wiring connections at the rear section of the specific unit or packaging scheme. So which needs to go where? Where should the connectors be? Where should the actual ventilation for the heating and the air conditioning schemes, where should they exist? All of this are identified at specific locations. So if you were to take a look at a typical desktop computer, you will make sense of what exactly I am speaking here. Okay. So on a desktop computer, for example, you'll have the power switch in one location, an indicator lamp in a particular location. You'll have some ports which are in front, some reset buttons are there, while towards the rear of that particular unit, you will see the presence of power connectors, various other data connectivity aspects such as USB ports and so on, accessory connection provisions that are provided. Along with that, you will also see the presence of a ventilation fan. Okay, radio scale implementation of a similar type will also be available in most of your notebook PCs. Okay, so what effectively is a package configuration is what you are seeing there. Okay, a similar scheme is followed even here. Only in this case, what is taking place is a functional subsystem or a module is identified as a packaging solution, so that in the event there is a problem, you can extract that particular boxed scheme of realization of the avionics subsystem and either service it or replace it. So that's the idea. Okay. So the use of standardized form boxes has led to the use of standard PCB sizes. So you don't have a concept where each computer, for example, has got a different motherboard configuration, a different ability to accept microprocessors and various other RAM configurations and so on. Okay, so here what you have is for the particular subsystem, there is a corresponding PCB, a printed circuit board design, which is most suitable. So the connector type is also defined there along with the mounting tray assembly and the internal layout design. All of these are clearly specified so that if there is a requirement to service, it can be done in the shortest possible time. If it requires replacement, the whole unit can be replaced in the least time that is available so that the aircraft can be brought back into service without too much in the form of a delay. Okay, so that's the idea of the ATR, air transport radio, which is specified as the Aeronautical Radio Incorporated, ARINC. Okay, so it is primarily helping with the process of standardization, and it has reached a point where connectors and cooling duct positionings are specified so in a manner where immaterial of the exact location of the vendor or the product that is being identified as a replacement solution anywhere in the world, there is the possibility to go for interchangeable deployment of such units. So for example, if there is a vendor in Japan and another vendor in the United Kingdom, if the aircraft happens to be in one or the other location and where it has malfunctioned at the level of a particular subsystem, the vendor in that particular region can provide a replacement solution for that. Okay, so different suppliers can provide the interchangeability for the specific product so that the aircraft can still be put into a serviceable level of operation. If one among you has your mic switched on for no express reason, please do turn it off. All right, so as an extension of the concept of the air transport radio, So the modular concept unit, MCU, is going to be an extension to the ATR, whose dimensions are principally 1/2 or 1.5 ATR okay. So in the case of the MCU, you would not have this varying uh, dimensions, which are corresponding to the complexity of the electronics that goes into a specific box dimension. Okay, so that if it is a half ATR, you have a less complex electronics in it. If it is a 1 or a 1.5 ATR, you have a large size PCB which has to be accommodated in such larger box dimensions. So that kind of a variability in the dimensions is reduced when there is a transformation in technology from the ATR to the MCU. Okay, so that is in its own standing a better solution than the more uh, traditional method, which is defined as a concept of the ATR. So in the case of the modular concept unit, you have implementation which goes in terms of the multiple units of the MCU constituting what is called as an one ATR. Okay, so you can have a greater deal of flexibility here, and the dimensions of the packaging scheme are identified in terms of the height, width, and depth, which are denoted in the units of inches here. So you can, for example, have 8 modular concept units constituting what is called as a single ATR. Okay, and if you have 4 MCUs, it is called as a half ATR implementation, and if you have 12, it becomes a 1.5 ATR. So what was previously a case of an ATR is now reduced into much more detailed implementation in the form of single MCU boxes, and you can have multiple such boxes which have now got a chance to be connected one to the next, or what is called as the integration exercise, which will lead to the concept of the ATR itself. Okay, so the unit level or the fundamental realization of the electronics is in what is called as a one MCU concept, modular concept unit. Okay. So larger avionics units and examples of such avionics systems include the air data and the inertial reference system. If they need to be combined with the inertial reference system, which has been obtained from external monitoring of various parameters, and such systems have to be interfaced with air data computer schemes, you will need to compulsorily switch to multiple realizations of this MCU in order to identify the entire avionics system. So examples include interfacing multiple avionics systems to achieve a common functionality. Okay, examples are the inertial reference system and the air data computer. So together they constitute what is called as a air data inertial reference system, and it has advantages because a unified representation of the aircraft attitude parameters as well as the navigational parameters can be obtained out of this. Okay, so one MCU is in effect given in terms of its dimensions in inches on the right hand side, and you may have multiple such units such as 8 MCUs constituting what is called as a one ATR, and the ATR is given as 8 times multiplication of the height, width, and the depth attributes. Okay, so the adoption of this MCU standard was closely related to the corresponding ARINC standard that was defined. Aeronautical Radio Incorporated 600, ARINC 600, defines a certain standard for the connectors, cooling ducts, and solutions for power connectivity that have to be identified at precise locations within each box. Okay, and the PCB has to be designed and deployed considering all of these attributes, and it goes all the way to the actual pin sizes that are identified for each of these connectors, the length of the wiring used, the material for the wires in terms of the dielectrics and the conductors that have to be implemented, the connectors which are used to terminate each of these wiring solutions that exist. Every one of this is precisely defined so that there is a certain standard that is imposed in the form of the modular concept unit and the larger scaling up of this MCU into the idea of the air transport radio, ATR. All right, so now let's look at what goes into each of these packaged schemes of realization of electronics, which will in turn identify itself within a region of the aircraft called the avionics bay. Okay, so the typical line replaceable unit, which is either in its very basic form implemented as the MCU or in multiple units of the MCU, what is called as the ATR. Either way, it is a line replaceable unit. Okay, so LRU principal architecture is what is shown here. So the LRU architecture has got in each instance of its realization a compulsory requirement for activating or energizing the various electronic components. And this is identified using the power supply unit, PSU. The standards which are defined for the power supply type signals are the 115 volts AC and the 28 volts DC. Okay, so these are the two which are primarily generated on board the aircraft. From there are possibilities to convert it down to something which is a TTL ready scheme, okay, which is the plus minus 5 volts and a 15 volt standard. So that is a scheme of conversion which is utilizable by the electronics, and that in turn is derived from a higher level of voltage that is specified for the aircrafts as 115 volts AC and a 28 volts DC. So your aircraft power plants principally will be generating signals at a higher level, and this will be down converted using DC to DC converters or converters that convert alternating to direct current in the standard of 0 to 5 volts and plus minus 15 volts. Okay, and these are used by the various microelectronic devices. The role of the processors and memory modules, they are primarily there to act in a manner where they will actually analyze and do various kinds of signal handling on the data that has been obtained from the various sensors after they are suitably digitized. Okay, and this all right, apologies for the small interruption. Let me continue with what I was discussing. So it had to do with the actual role that is played by the processors and the memory modules. They function in a manner to communicate with the various input and output modules, and they use a dedicated pathway for communication, which is called as the processor bus, okay, or the data link, or the highway for communication, which is exclusive for information that is being transported from the input and output modules to the computational parts of the LRU. So that is effectively rendered in the form of a transmission pathway called as the processor bus. The real world is usually identified as the information that is being collected from the sensors on the right hand side, and these are being subjected to the various tasks which are primarily defined in the processor and memory units. So you have information which has been obtained from the regions on the right hand side, which is the real world or the practical information available regions of the electronic system, and these are converted into a form where they are subjected to various algorithms and processing. Okay, so the real world is effectively identified in this diagram on the left hand side to the LRU interfaces with the processor bus, and this is taking place making use of a variety of input and output devices that convert the analog real world information into its digital form. And in the reverse manner, if they're required to be visualized or some amount of information regarding the magnitude of the measurement needs to be made, you have again a conversion back into the analog form, okay, as we had seen in one of the earlier discussions. So the right section of the LRU interfaces with the other LRUs by means of a digital data bus. Examples of these data connectivity options include the ARINC 429, and various other standards such as the 629, military standard 1553B, and so on. Okay, so these are the very commonplace databases that are used in avionics system in current times. Okay, and these have had their advent from quite a while back onwards. So we'll also be looking at various of the other modules that find a place in this particular slide. For example, if there is a requirement to convert analog inputs to digital form and digital back into analog, which are primarily to do with the various sensors and processing solutions. The ADCs and DACs help with that task, and there are aerospace defined standards for these analog to digital conversion schemes, okay, which effectively do sampling, quantization, and modulation. Okay. Other than that, you also have a mention of what is called as a synchro. Okay. By and large, most of the information is derived from rotational movements that are there in the aircrafts. Okay. So all the various types of movements that you notice are principally of the rotation kind. So there is a requirement to convert or identify the extent of this rotation that has taken place, such as if it is the power plant and the engine, the shaft of the motor or the dynamo that is used to either generate mechanical energy or generate electrical energy, one way or the other. Okay, how much has the typical rotation been? How many rotations have taken place per unit time? All of this requires to be constantly monitored. That in turn helps to obtain a certain sense of the actual performance aspects of the aircraft's power generation attributes. Okay, so that's the idea why there is a module called the synchro. So the resolver is another name for the synchro. It is primarily a transducer that converts angular position and angular velocity, which is a change in angular position with time, of the rotating shaft into its corresponding electric signal. Okay, so if there is so much of change in angle of the rotating shaft of the engine as a function of time, so that is broken down into a series of steps and encoded depending on the finer level of detail that one needs to have. Is it monitoring that is happening at the rate of 10 degrees, or is it 1 degree steps, or is it a fraction of a degree? Depending on that, you'll need to convert it into a suitable digital equivalent. Okay, as the number of bits increases, the ability to identify smaller levels of change in angle is also a possibility. So that's the idea of the resolver or the synchro. It creates a transduced representation for the equivalent angular position and angular velocity of the shaft into its corresponding electric signals. And while they still remain in the analog form, there is a requirement to convert it into the digital equivalent using the encoders and the decoders. Okay, so the delivered signal is proportional to the sine and the cosine of this shaft angle. So the synchro to digital converter, SDC, is used to convert these signals to the corresponding digital output, which corresponds to the shaft angle and the shaft velocity parameter. Okay, so effectively, any attribute associated with rotation, it may be that of a power plant, or it may also be those of control surfaces. So how much of a turn which will deploy a suitable control surface such as a flap or a rudder, how much degree of turn has to be given in order to bring about a complete maneuver in the aircraft, so that it makes a certain turn or a dive or a climb downwards or a descent or an ascent. Okay, all of this is primarily realized in the form of a deployment of a suitable control surface. So that is again requiring a monitoring of the angle or a specific control to be given in order to realize a certain magnitude of the control surface deployment. Okay, either way, you have a conversion from analog to digital that has to be taking place, synchro to digital converters, and the conversion back into analog form is effectively rendered here. So discrete or digital inputs are obtained as equivalents of this conversion from analog to digital representations. So the modules on the left-hand side that you see are all going to be various such data transformation outcomes that exist, while principally all of the real-world data is being processed by taking it across suitable connectivity solutions which are enabled in the form of the data buses. And you have 429 standards. Along with that, 629 as well as 1553B standards are also available side by side And depending on the level of sophistication that is expected, you have various data buses which can be accommodated within a specific type of the LRU configuration, be it in the form of the ATR or the MCU. So let's now take a look at some of the typical avionics systems that are on top of an aircraft. Okay, and it is not that every one of this system has to be there within an airplane. Depending on the mission and the role the aircraft performs, you will have a few or many of these subsystems. Some of them are critical to the aircraft and they cannot be really considered as optional, while there are several others which are optional systems which will primarily find a place on board the airplane depending on the exact nature of the mission that the aircraft is carrying out. Okay, and the mission is primarily defined as the purpose and the activity that is identified for a given aircraft, and it is primarily taking to the air in order to accomplish this mission. Okay, so let's start with the flight management system. It is an automated, computationally driven scheme that will help the aircraft to precisely conduct navigation as per the intentions of the person who is controlling it. Okay, so the primary function is managing the various aspects of the airplane, especially the control surfaces and so on, and carefully monitoring the overall platform that is flying in a manner where it is able to execute an event-free or uneventful flight. Okay, that's primarily what is the expectation out of any flying aircraft. It shouldn't be really beset with lots of circumstances which will literally incapacitate it. An uneventful flight is the best possible case of a very well managed airplane flying attribute. Okay, so flight management system is a fundamental component in aircrafts as a realization of avionics. Okay, so the dedicated computing system that can perform a variety of tasks while the aircraft is in flight in a manner where it will typically reduce the workload on the human element and also take away critical roles and automate it in a manner where the aircraft can be safely in flight. So that's the idea of the flight management system. So in order to accomplish this, data from GPS, inertial navigation schemes, radio frequency navigation parameters all have to be acquired, processed, as well as displayed, so that the user friendliness of the displayed information can alone be taken up by the pilot in order to proceed with carefully navigating the airplane. So that's the primary idea of the flight navigation system. What is the inertial reference system? So on board the aircraft, you have data which are being acquired from beyond the Earth, that is from deep space. Okay. Examples include star formations, the typical orientation of very prominent stars which are in space have to be consulted, and the X, Y, and Z axis, for example, as the cardinal axis for orientation of the corresponding aircraft lateral and longitudinal axis parameters also has to be referenced with respect to the orientation of stars. Okay, so this cardinal axis as X, Y, Z axis, for example, are primarily oriented while the aircraft is on the ground by precisely reorienting it towards the very prominent star formations which are in space. And there are a collection of stars which are consulted for this. With reference to that, a group of stars is always available in order to precisely orient the X, Y, and Z axis. A version of this is carried on board the aircraft in the form of an equipment called the gyroscope. So the gyroscope will always maintain this axis, and if the aircraft were to change its orientation, it can always be with reference to this axis which is already set on the ground and carried on board the aircraft using the gyroscope. Okay, so this referencing scheme, which is independent of anything on board the aircraft and is primarily set once for all by consulting space-based schemes for referencing, is called as the inertial reference system. Inertial is because it is non-accelerating. So it is a constant velocity scheme, which means, as an example, if I can give you, the more distant the object is while it is moving, the more stationary it appears. At the same time, an object of comparable speed, if it were very close by, it will be perceived as moving faster. Okay, and if you can take this idea all the way to the very limits of space where you have stars which are located, stars, even though they are moving, because of the sheer distances involved, they appear to be stationary. Okay, and they remain almost without a change for several hundreds and thousands of years. So with that understanding, if you can now orient your XYZ axis with reference to those stars, and not any star, but very carefully selected groups of stars, you can certainly consider this as a precise referencing scheme or a coordinate reference scheme against which the actual changes in the aircrafts can now be determined exactly. So if there is a change by a certain pitch or a yaw or a roll by so many degrees, it can effectively be understood in a better manner. So that's the idea of the inertial reference system. All right, so we'll be looking at the first levels of understanding of every one of these following systems in the next session for this course, which will be on Thursday. Today's session stops right here. If there are any queries from your side, you can ask them now. All right, we stop today's session with this particular slide, and we'll have a continuation of what has been discussed today in this session on Thursday.